In this paper, we present a novel concept of a climbing robot that uses an optimal control strategy to overcome an obstacle and reach a desired target on a slanted or a vertical mountain wall. The resulting motion of the robot depends on two mechanisms: 1, the impulsive pushing force exerted on the wall, and 2, the retraction force applied by a winding, unwinding rope mechanism. The jump between two positions is computed via optimal control. The problem is tackled using the indirect variational approach with the Pontryagin maximum principle. We formulated the optimal control problem as a Bolzan problem, subject to ordinary differential equations and bounded controls, with constraints on the states, control, and boundary conditions. The problem has 6 state variables derived from the cylindrical coordinates of the system, namely, theta, phi, and the rope length L, and their respective derivatives. In addition, there are 3 control variables: the force applied to the wall for jumping, which is decomposed into tangential and normal components, and the winding force of the rope. The jump forces are shaped with a Gaussian function to simulate their impulsive nature. The system's dynamics are obtained using the Euler-Lagrange equation. The optimization target function has the Mayer term, which includes a weighted sum of the final time and final kinetic energy, and the Lagrange term, which contains the rope retraction winding force contribution. The problem is constrained with subject to the states and control inputs. The first bound is set on the retraction force that can pull but not push the rope. Another important constraint limits the actuation force for the jump. Connected to it is the friction constraint, which relates the tangential and normal force impulse. The last 2 constraints are included to ensure that the motion is in front of the wall and not inside the mountain, and to model the wall's surface. We present simulation results that show how the control inputs obtained running the optimization are able to bring the robot to a desired target. In the first experiment, we show a validation of the trajectory in a MATLAB environment with the simplified model. Then we perform the validation with the full 9 degrees of freedom model, showing that the simplified model is a good approximation to plan jump motions that do not involve angular motions. The small error at the target is due to the discrepancy between the models, and the lack of a controller, which are part of future works. Before the liftoff, the leg reorients in the impulse direction to avoid the generation of centroidal moments that would start pivoting motions about the rope axis. Next, we show jumps to different target points from the same liftoff location on the wall. In this experiment, we initiated the jump lifting off from the rock pillar, demonstrating the approach is effective also for slanted surfaces. Finally, we discovered that the achievable targets are affected by the friction coefficient at the liftoff location. Therefore, we performed a reachability analysis to numerically derive a region of reachable targets. You can see that there is a limited number of targets that are reachable out of the friction boundaries and that they involve high energy consumption from the retraction mechanism.